Derivatives and the shapes of curves. Goals here, understand the mean value theorem. We're going to see this relates the instantaneous rate of change to the average rate of change on a curve. Know how to use derivatives to identify intervals of increase and decrease. Know how to use derivatives to identify intervals of concavity. And then last but not least, understand how to use the first and second derivative tests. So we're going to see that these derivatives can help us identify where the maximum and minimum locations are on a graph of a function. So the mean value theorem, basically we're going to have some function here that's differentiable, so some f of x. And remember, differentiable means that the derivatives exist. And if it's differentiable, it's also continuous. So this function is a differentiable, a continuous function on the closed interval a to b. And if that's true, then there exists a number c in the open interval a to b, such that the f prime of c, the instantaneous rate of change at some point c, is going to be equal to f of b minus f of a all over b minus a. And that right side, it's the slope formula. And more importantly, it's the slope between the a and the b endpoints for this function. And if you remember the use of the slope, it gives us the average rate of change. So what this is saying is that the instantaneous rate of change at some point in the interval is going to be the exact same as the average rate of change over the entire length of the interval. And if you think about driving around, this should make sense. If you're driving around town for a couple hours or something, running errands, let's say your average speed was like 35 miles an hour. Well, it should make sense that somewhere as you're driving around town, your speedometer was exactly reading 35 miles per hour. That's basically all this is saying. Now visually, we can look at this in a graph, something like this, where maybe you got your interval a to b going from here to here. And if you connect those 2 points with a straight line, that secant line, you get an average rate of change from the slope of that line. And then just looking at the graph here, there's a couple of places, here's one of them, where the slope of the tangent line again is that first derivative, but that slope of the tangent line is the same as the slope of the secant line. And you get another place maybe about right in there-ish, where that slope of the tangent line is the same as the slope of the secant line. So really that's all that the mean value theorem is saying, is that somewhere in the interval, the instantaneous rate of change will match the average rate of change. And it could happen in a couple of places as it did here, or more. Okay, so let's take a look then at increasing and decreasing functions. So one thing to recall is that the derivative f prime of x will give the slope of the tangent line to the curve for some x equals a. We talked about this a little bit up above, coming back again. And also recall that a function is increasing when its slope is positive and decreasing when its slope is negative. So if we put these facts together, what we end up with is that f prime of x, when it's greater than 0 on an interval, then the f of x is increasing on that interval. And on the flip side of that, you got your f prime of x being less than 0 on an interval. That's going to indicate that f of x is decreasing on that interval. So that's all there really is to it. When your derivative is positive, you know you're increasing. When your derivative is negative, you know you're decreasing for whatever x's produce those greater than or less than values. All right, so let's change gears again here and get into concavity. So the concept of concavity, we've talked about this a little bit before, but let's bring this back with a little picture here. So something like this, go out like that. And on the left side here, I'm going to start where you are cupped up. You are what's called concave up. So we got concave up right here. And then next to that, we got concave down. And somewhere between concave up and concave down, we changed our concavity. And it'd be maybe right about that point right there. We'll see how to find these later. But we call those changes in concavity inflection points. So this is an inflection point here. And technically, there's another inflection point over here on the right where we change from concave down to concave up. So again, the inflection point is where you change concavity. And because of that definition, this little cusp point here where it's kind of spiky in the middle of the graph is not an inflection point. It's concave down on the left of it, concave down on the right of it. We did not change concavity, not an inflection point. Okay, another thing to notice about these concave up, concave down regions is that there is something going on with the slopes. And if you look here at the tangent lines, the slopes of the tangent lines to the curves, notice that the left side here of the concave up, and that one's just a little up, we'll put that in there, it's decreasing. So you got a negative slope there. And then it gets less negative until it gets to 0 at that minimum. And then it starts increasing on the other side, getting positive slopes. So this is always going to be true. Something I want you to be aware of is that when you have concave up, the slopes, or the f prime of x's, your f prime is your slope, is increasing over the region where it's concave up. As you move left to right, the slopes will be increasing in that concave up area. And then similarly, in the concave down, if you look at the slopes of the tangent lines as you go around that concave down part of the graph, going from left to right, notice that we started out positive on the left of the concave down, and then it got less positive, it got to 0 at the max, and then it went negative, and then it gets more negative. So whenever you have concave down, the slopes, the f prime of x values, are going to be decreasing. So we'll see how to put this into play a little later, but keep in mind, if you're looking at the slopes are increasing, the slopes are decreasing, your f prime of x is increasing, your f prime of x is decreasing, what you're really talking about there is a change in the f prime. To measure the change in your first derivative, you use the second derivative. So we're going to start seeing here with the concave up and concave down, there's going to be a way to use our second derivative in order to indicate those places. So since the concavity is determined by that rate at which a slope is changing, we can think of it as the rate at which the derivative is changing, just restating that piece from that last slide. And this rate is given by the second derivative. So in general, if your second derivative is greater than 0 for all x in an interval, then the graph of f of x is concave up. Looking back at this picture, the slopes were increasing on that concave up part on the left. The slopes increasing represented by the change in f prime, which is given by f double prime. And for increasing, you look at greater than 0. So if your f double prime is greater than 0, f of x is concave up. And similarly, if your f double prime is less than 0 for all x's in an interval, then the graph of f of x is concave down on that interval. So your slopes are decreasing around that concave down part. Your f primes are decreasing, which means that f double prime will be less than 0. Okay, so let's take this information and see if it can help us find maximums and minimums. So if we look at the first and second derivative tests here, what we'll see, and again, some kind of graph like this, we got a little concave down area here. Get this into play. We've got a concave up area over here. We have, looking at this concave down part, there is a maximum there. You have a local max at that location. And the local max, in this case, you would have f prime equal to 0. So your first derivative would be equal to 0 there, 0 slope. But notice also on the left of the concave down, and to the left of that local max, you've got f prime being greater than 0. The slopes are increasing. And on the other side, you've got f prime being less than 0. So you're decreasing. So one thing that we're going to see here is that there is something to be said about when your first derivative changes from increasing to decreasing, you're going up and then you turn around and go down. It should make sense. You've reached a high point before you started going back down. And we're going to see that this concave down, f prime, or f double prime, sorry, less than 0 is going to help with that as well in one of the tests. So if we look at the concave up area, notice that right here we have a local min at the bottom of that little valley there. The f prime is equal to 0 there at that local min. And notice that as we come in on the left side, we actually have the f prime being less than 0 still, it's decreasing. And then we change on the other side at local min to f prime being greater than 0. So now we're seeing if we go from decreasing slope to increasing slope, or more importantly, the function is decreasing and then changes to increasing, indicated by the derivatives, then we're going to see a local minimum at that change in the sign of the derivative. It goes from negative to positive. Oh, we got a local min there. And also notice concave up, we could represent that with the second derivative being greater than 0. Okay, so those little pieces of information are going to come into these tests. So we can use the derivatives to determine whether or not a function has a local max or a local min at a critical number. So we still have to find the critical numbers, and went over this in a prior video. But if you find the critical number of a continuous function f of x, then you can go through these little kind of bullets here and see if you've got a maximum, minimum, or none, as indicated by what's happening with your derivatives. So if f prime of x changes sign from positive to negative, so you're going up and then you're coming down, and it changes sign at that critical number, then f of x has a local max at that critical value. Similarly, if f prime of x changes sign from negative to positive, so you're going down and then you start going back up at that c, then the f of x is going to have a local minimum at that c. And if f prime of x does not change sign at c, then there is no local maximum or minimum at c. You could think of the x cubed graph as something like this, where it's increasing, flattens out, and then increases again. Right there at 0, you've got that place where it is a critical value for the derivative, the slope of 0, but the sign doesn't change for f prime on either side of it, so there's no local max or local min there. Okay, first derivative test is good, but the second derivative test could be more powerful when it is able to be used, and we'll see this pick up in part 2 of this video.